Hello, my name is Chen Jing. Today I'm going to introduce you an agricultural model that I used during my research, the name of which is called Root Zone Water Quality Model. To start with this topic, first we need to know what this model is. The Root Zone Water Quality Model is a one-dimensional model consisting of hydrology, nutrition, pesticide transport, transformation, crop growth, measurement practice components. It has been tested in many countries and it is now being commercialized. To better understand what this model is and how it works, well, let's take a look at a case study that I did work on last year, simulating the drainage and crop yield in the subsurface drainage field in southern Quebec. So the objective of this study is to evaluate the performance of Root Zone Water Quality Model in simulating the drainage flow and crop yield under different water table management and nitrogen applications. So in this research, I focused on two water table management practices, which are the free drainage and controlled drainage with subrogation. In a free drainage system, the drains are laid out at a certain depth to remove the excess water. In this system, the farmers have no control over the flow of water leaving the field. However, in the controlled drainage system, the farmers can open the drains to remove the excess water from the field or in the wet periods, or they can close the drains to retain soil moisture when drought is forecasted. In order to have more control over the soil moisture, the subrogation can be done in conjunction with the controlled drainage. And here's the experimental layout of the field study. The blue blocks represent the free drainage and the green ones are the controlled drainage with subrogation. For the modeling part, the input data includes the weather data, the crop information, soil information, and management practice. And the outputs are the drainage rate and crop yield, the soil moisture content, the water table depth, etc. And here the table shows the chemical parameters that needs to be calibrated. These parameters can be classified into two categories: P1, P2, P5, PHINT mainly affect the crop's phenology, while the left affect the crop's growth traits, such as the crop yield and the crop's biomass. And here's the soil hydraulic parameters that needs to be calibrated based on the measurement of soil texture, soil profile, and soil water content. And there are some other parameters that needs to be calibrated, such as the soil albedos and the nutrient components, to have a better simulation of the crop's ED transpiration, mineralization, and the denitrification. So here we come to the result. This is the soil water content, and the curves represent the simulated results, and the observed ones are the dots. So the same thing for the water table depth. Here is the drainage rate. In general, the model simulates well the drainage rate, except a little bit overestimation in spring because of the snow melt. And here's the leaf air index. So the model simulates very perfectly with the leaf air index. And for the crop yield, the model that also does well, except a little bit under overestimation for the controlled drainage with subrogation in the year of 2009. So in conclusion, this calibrated model simulated very good in the subsurface drainage and the crop yield under different water table management practice and different nitrogen applications. And this model is a very good tool to study the agricultural system with less time and cost. So in the future study, I'm going to continue to use this calibrated model to investigate the long-term impact of the climate changes on crop growth. And my references, thank you all for your attention.